Hello everyone, I'm really pleased to present the Efficient Graph Neural Architecture Search for Medical Imaging in Real-World Clinical Setting paper that is published with the ICML workshop Muslim in Machine Learning. So we all know that AI for medical imaging delivers impressive results and has been there for quite some time already. So you can see skin lesion classification, organ segmentation, brain tumor segmentation, and these are only some of the tasks that AI can do and deep learning can do. Now, although these are major tasks where AI can truly bring added value in medicine and radiology specifically, but its adoption remains limited by on-the-ground technical constraints. So actually, radiologists on the ground are not really using it. So these algorithms require significant memory, so they require laptops with some with some amount of resources. So significant memory, high-end GPUs for some of them. Their model sizes exceed the capacity of clinical machines or laptops that are usually used, and the inference time takes often quite a lot of time. So at the end, the radiologist prefers to analyze the image themselves rather than relying on these kind of engines. Now, the issue with it is that the standard models that are used exceed the 1 gigabyte of memory. And if you're a radiologist that deals with multiple images coming from different tasks that you can see here, for example, thoracic pathologies, diabetic retinopathy, 3D organs recognition, and 3D pulmonary nodule classification. So if you have to do all of these tasks in one day, then you have to go back and forth between one model to another. So you have to use like these significant large models that all includes an encoder part that takes the image, extract all the features, and then a task-specific predictor that will detect the nodule or will detect which organ we're dealing with. And of course, if you have one computer, then you have to have enough memory to host all of these different models. And of course, this is just a sample. These are 4 tasks, but in reality, you have to do a lot more than that. So the first solution that was actually published in quite some papers is to share the encoder part. As you can see here in this slide, you can see here in this figure that the encoder is now shared across the different tasks. And this is possible because actually medical images share quite some features, and we can extract different features from these different images. And then we will predict or have different task-specific predictors that are trained separately for each of the different tasks. So this is a first solution. This significantly decreases the amount of memory that is required in a laptop or in a clinical machine, but it's still quite some large. So these task-specific predictors are still large enough to overflow the memory of the user or the practitioner. So our contribution is to focus on these heads. So in an all tasks shared memory, so you can see here in this graph, when you compare the number of parameters of the all tasks model, you can see that these heads takes quite some percentage there. You can see 23%. And this, of course, increase when we increase the number of tasks we want to do. So this is only for 4 different tasks. We have 23%. But if you look at 10 different tasks, then it goes to the 40% and it goes to a significantly higher number. So we want to deal with these heads or these task-specific heads, and specifically we want to explore, can we design a lighter version of these heads, leveraging graph-based components or graph-based neural networks. So for this, we design this kind of framework where, given a task, we use this encoder as is, because this is a shared encoder that's going to be used for all the different tasks. And then what we are going to do is we're going to create a graph neural network for the head of each of these different specific tasks. So we change the topologies of the input, we create the input graph that is given to the neural network, and we try to fetch which combination of different blocks we can create to get to the optimal neural network, or to get to the optimal head. So creating this combination, of course, we deal with different objectives. We want the smallest possible network. So in terms of number of parameters, we want the smallest possible, but we still want the highest in terms of accuracy. And here it's AOC in particular because of these different tasks we're dealing with. So we're actually doing a Pareto optimization in there to optimize this differentiable search and to get a trade-off, an architecture that is better in terms of trade-off between the different objectives here. So as you can see here in the results, we are actually outperforming different state-of-the-art models in the multitask scenario and even in the single task. So you can see here, for example, in the single task MedNIST 3D, we can find a model that is way smaller in terms of memory. So it's like divided by 2 compared to what we can see in the literature. But you can also see that it's, in terms of accuracy, it also beats the different state-of-the-art models. And you can see that our multitask, although it's not the best in each of the single tasks, but it still like encompasses a great accuracy at the end for the different tasks. And it's also way smaller than the different models themselves. What we did, because we have a collaboration with an Algerian ENT doctor, so we took our multitask model and we tested it in a concrete scenario, which is a tumor detection out of the MRI image. And you can see here the tumor confidence that is given by our multitask network. So it detects 78% similarity between the ground truth, the annotated by the doctor, and the prediction. It is quite impressive, given that the model is not trained for this task specifically. It is trained for a generic number of different tasks, but yeah, it can detect here the tumor quite confidently. Now, the takeaways is that EGNAS, we are introducing a novel framework that is Pareto-efficient, so it constructs architectures or task-specific heads for medical imaging tasks. It is, of course, leveraging the multitask framework or the multitask scenario where we have a shared encoder and we're trying to detect, or we're trying to construct each of the specific heads for each of the tasks. Across all the different tasks, we can see that our memory usage is divided by 2. And our networks don't outperform or even achieve similar results as the state-of-the-art models across all the tasks. Now, our future work includes designing a specific data set for these ENT tasks, because these ENT tasks are so small and we cannot find a general or public data set for them. So we want to first focus on creating the data set and then creating models based on these data sets or specifically for these data sets. Thank you very much.